Of gamma f y plus the average gamma f like that plus so forth. I usually call that y beta. So this is the value of y. When the point is within the averaging volume. Well, so there is a lot of discussion about what are the values of those parameters. And so I published a series of papers in the 90s about that. But so what can we say is essentially I have something, this is the epsilon f. Oops. Here. This is epsilon f times PFF plus this is almost zero, negligible for actually this is zero if the volume V beta has symmetrical properties, for instance. So it's, if this is the center of gravity of the X is the center of gravity of the volume beta. There are additional difficulties if you are working with a periodic medium, but this has been discussed thoroughly in those series of papers. So basically, this is a quantity which is negligible, so zero, and those here you cannot get that property because, for instance, if you have a y x times yx, then it's a square, so it can be zero. So this is something which has a finite value, and then but that finite value depends on the size of the derivative. So we have basically something like that, s over square over L square times some estimate of the average value. So this is where the assumption of separation of scale holds. So we have here, this actually is not equal to that, but this is a correct approximation, providing that the separation of scale assumption works. So essentially we get that the average of an average value is the average. So the average values, all macro scale values, can be extracted from averaging operators. But this is not exact, so we have to verify that this is not the case. So here I made, for instance, the assumption that this grad is sort of triggered by the large scale, the macro scale value, but it can be something which is process dependent. So if you have, for instance, a porous medium and then a temperature field, you just impose, for instance, a Heaviside condition here, then you will have at the beginning a characteristic length scale, which is much smaller than this one. But we are considering the large scale problem, so most of the time LT can be assumed to be equal to 1. But this is, we discussed that already this morning. This is process dependent, so you have to verify that you are manipulating the correct length scale and time scale in the system. So this is the first approximation that is used in all the developments that Professor Pila will do and I will do also myself. And there are some additional things. Well, if now you use that, then if you take the average of the decompositions, you will have the average here, and so you get that the average of a deviation is 0. Once again, this is not an exact, contrary to the averaging theorem, which are exact. This is not exact, this is an approximation that depends on the separation of scales. And there is another one which is which you find everywhere. You will use that. I will use that also in the second part of the course, which is what about the average of a gradient. So the average of a gradient is what Pierre is introduced for the pressure. So this is epsilon times grad plus the grad of the pressure, and the intrinsic pressure times the grad of the porosity. And then I have this term. If I introduce the deviation here, the decomposition here, I have two terms. And this term, now I can do the same type of analysis I've done before. I can introduce Taylor expansions and then look at all those the approximation that are related to the assumption of separation of scales. And it turns out that, like I've done before, I can extract the average value. This is an approximation, I'll do that. So I can extract the average value from the interface and get something like that. And it turns out that this integral actually is minus the gradient of the volume fraction of the beta phase. So there is something very important. Each time I have the average of a gradient, actually I can have the volume fraction of the phase times the gradient of the average value, plus an integral that depends on the deviation and not the entire field. This is something very important. Once again, this is an approximation, but which is very, very, very important. And to come back to the comment here, I never use the fact that the gradient of the pressure is zero over the system. So this term cancels because of that. Therefore, this is essentially what you essentially assume is that the average fields are linear over the averaging volume, not constant, by the way. This may be used from over application. In general, you don't need that. But you need to, of course, to be able to manipulate that approximation. You need to cancel that, and this is not cancelled by looking at these terms. It's cancelled by looking at the ratio of the length scales for those two terms. So that's the thing you can say about that particular series. So all those approximations are used all the time. Each time you will start working on a problem, you will have to look at things like that.
Has there ever been a case where the first term is retained, where I guess the first moment is not zero, and then you keep it?
Yes, that's they are. I published several papers on that problem. It's not always the case that you can cancel that. So there might be theories in which you will keep those terms in the system. I mean, I have several examples. I worked on two-phase flow in heterogeneous media. To get those terms zero, the medium must be random, for instance, which is not always the case. And so if it is not the case, you can keep those terms in the analysis. But what you will get is something, a term here, that will depends on the size of the averaging volume. So the size of the averaging volume will pops up in the macro scale model you will develop. Let me give you an example. This is in petroleum engineering, for instance. People are working with, even if you have a slightly compressible fluid, since you have a huge reservoir, the density, viscosity may change. So I may have something like that. So what do I do? Of of such things. In the usual, either rho beta can be constant, but it's not the case for many fluids. So I do exactly the same. So this is rho beta, p beta. It's a short notation for the intrinsic pressure. You may want to, in the usual thing, applications, we discard this term. On the basis that it will show that P beta is small compared to the deviation is small compared to the pressure. Well, but P beta is still varying over the system. So I have potentially density variations because the average pressure changes over the averaging volume. So same stuff, I do the same. I will, this time, when I do the averaging, I will have something like that, plus so this account for the variation of the average pressure over the averaging volume. And you may want to keep that in your analysis. So you will have, for instance, a transport property that will depend, or equations that will depend on that, and there will be R0, the size of the averaging volume within the system. So if you, this is classical, for instance, for effective parameter. When you work with, you do subsequent upscaling between Darcy scale and large scale. In many cases, the effective properties depend on the scale of the averaging volume because the saturation changes over your domain or density or whatever. So there are not many theories like that because then you have to be very careful about the size of the averaging volume. So there are many different things. And then there are a few papers in the literature which do incorporate such effects. So, but that's really advanced compared to the discussion this morning.
Okay, so I think we will kind of take a break. This separation of scales. So we'll come back and then. So I think coffee is there. We can